A laser is a device that emits light through a process of optical amplification based on the stimulated emission of electromagnetic radiation. The term laser originated as an acronym for light amplification by stimulated emission of radiation. The first laser was built in 1960 by Theodore H. Mayman at Hughes Laboratories, based on theoretical work by Charles Howard Towns and Arthur Leonard Shaulow. A laser differs from other sources of light in that it emits light coherently. Spatial coherence allows a laser to be focused to a tight spot, enabling applications such as laser cutting and lithography. Spatial coherence also allows a laser beam to stay narrow over great distances, enabling applications such as laser pointers. Lasers can also have high temporal coherence, which allows them to emit light with a very narrow spectrum, i.e., they can emit a single color of light. Temporal coherence can be used to produce pulses of light as short as a femtosecond. Among their many applications, lasers are used in optical disk drives, laser printers, and barcode scanners, fiber optic and free space optical communication, laser surgery and skin treatments, cutting and welding materials, military and law enforcement devices for marking targets and measuring range and speed, and laser lighting displays in entertainment. Fundamentals. Lasers are distinguished from other light sources by their coherence. Spatial coherence is typically expressed through the output being a narrow beam, which is diffraction limited. Laser beams can be focused to very tiny spots, achieving a very high irradiance, or they can have very low divergence in order to concentrate their power at a great distance. Temporal coherence implies a polarized wave at a single frequency, whose phase is correlated over a relatively great distance along the beam. A beam produced by a thermal or other incoherent light source has an instantaneous amplitude and phase that vary randomly with respect to time and position, thus having a short coherence length. Lasers are characterized according to their wavelength in a vacuum. Most single-wavelength lasers actually produce radiation in several modes having slightly differing frequencies, often not in a single polarization. Although temporal coherence implies monochromaticity, there are lasers that emit a broad spectrum of light or emit different wavelengths of light simultaneously. However, all such devices are classified as lasers based on their method of producing light, i.e., stimulated emission. Lasers are employed in applications where light of the required spatial or temporal coherence could not be produced using simpler technologies. Terminology. The word laser started as an acronym for light amplification by stimulated emission of radiation. In modern usage, the term light includes electromagnetic radiation of any frequency, not only visible light, hence the terms infrared laser, ultraviolet laser, X-ray laser, and so on. Because the microwave predecessor of the laser, the maser, was developed first, devices of this sort operating at microwave and radio frequencies are referred to as masers, rather than microwave lasers or radio lasers. In the early technical literature, especially at Bell Telephone Laboratories, the laser was called an optical maser. This term is now obsolete. A laser that produces light by itself is technically an optical oscillator rather than an optical amplifier as suggested by the acronym. It has been humorously noted that the acronym LOSER, for light oscillation by stimulated emission of radiation, would have been more correct. With the widespread use of the original acronym as a common noun, optical amplifiers have come to be referred to as laser amplifiers. Notwithstanding the apparent redundancy in that designation, the back-formed verb to laser is frequently used in the field, meaning to produce laser light, especially in reference to the gain medium of a laser. When a laser is operating, it is said to be lasing. Further use of the words laser and maser in an extended sense not referring to laser technology or devices, can be seen in usages such as astrophysical laser and atom laser design. A laser consists of a gain medium, a mechanism to energize it, and something to provide optical feedback. The gain medium is a material with properties that allow it to amplify light by way of stimulated emission. Light of a specific wavelength that passes through the gain medium is amplified. For the gain medium to amplify light, it needs to be supplied with energy in a process called pumping. The energy is typically supplied as an electric current or as light at a different wavelength. Pump light may be provided by a flash lamp or by another laser. The most common type of laser uses feedback from an optical cavity, a pair of mirrors on either end of the gain medium. Light bounces back and forth between the mirrors, passing through the gain medium and being amplified each time. Typically one of the two mirrors, the output coupler, is partially transparent. Some of the light escapes through this mirror. Depending on the design of the cavity, the light coming out of the laser may spread out or form a narrow beam. In analogy to electronic oscillators, this device is sometimes called the laser oscillator. Most practical lasers contain additional elements that affect properties of the emitted light, such as the polarization, wavelength, and shape of the beam. Laser physics. Electrons and how they interact with electromagnetic fields are important in our understanding of chemistry and physics. Stimulated emission. In the classical view, the energy of an electron orbiting an atomic nucleus is larger for orbits further from the nucleus of an atom. However, quantum mechanical effects force electrons to take on discrete positions in orbitals. Thus, electrons are found in specific energy levels of an atom, two of which are shown below. When an electron absorbs energy either from light or heat, it receives that incident quantum of energy. But transitions are only allowed in between discrete energy levels such as the two shown above. This leads to emission lines and absorption lines. When an electron is excited from a lower to a higher energy level, it will not stay that way forever. An electron in an excited state may decay to a lower energy state which is not occupied, according to a particular time constant characterizing that transition. When such an electron decays without external influence, emitting a photon, that is called spontaneous emission. The phase associated with the photon that is emitted is random. A material with many atoms in such an excited state may thus result in radiation which is very spectrally limited. But the individual photons would have no common phase relationship and would emanate in random directions. This is the mechanism of fluorescence and thermal emission. An external electromagnetic field at a frequency associated with a transition can affect the quantum mechanical state of the atom. As the electron in the atom makes a transition between two stationary states, it enters a transition state which does have a dipole field, and which acts like a small electric dipole, and this dipole oscillates at a characteristic frequency. In response to the external electric field at this frequency, the probability of the atom entering this transition state is greatly increased. Thus, the rate of transitions between two stationary states is enhanced beyond that due to spontaneous emission. Such a transition to the higher state is called absorption, and it destroys an incident photon. A transition from the higher to a lower energy state, however, produces an additional photon. This is the process of stimulated emission. Gain medium and cavity. The gain medium is excited by an external source of energy into an excited state. In most lasers this medium consists of a population of atoms which have been excited into such a state by means of an outside light source, or an electrical field which supplies energy for atoms to absorb and be transformed into their excited states. The gain medium of a laser is normally a material of controlled purity, size, concentration, and shape, which amplifies the beam by the process of stimulated emission described above. This material can be of any state: gas, liquid, solid, or plasma. The gain medium absorbs pump energy, which raises some electrons into higher energy quantum states. Particles can interact with light by either absorbing or emitting photons. Emission can be spontaneous or stimulated. In the latter case, the photon is emitted in the same direction as the light that is passing by. When the number of particles in one excited state exceeds the number of particles in some lower energy state, population inversion is achieved and the amount of stimulated emission due to light that passes through is larger than the amount of absorption. Hence, the light is amplified by itself. This makes an optical amplifier. When an optical amplifier is placed inside a resonant optical cavity, one obtains a laser oscillator. In a few situations it is possible to obtain lasing with only a single pass of EM radiation through the gain medium, and this produces a laser beam without any need for a resonant or reflective cavity. Thus, reflection in a resonant cavity is usually required for a laser, but is not absolutely necessary. The optical resonator is sometimes referred to as an optical cavity, but this is a misnomer. Lasers use open resonators as opposed to the literal cavity that would be employed at microwave frequencies in a maser. The resonator typically consists of two mirrors between which a coherent beam of light travels in both directions, reflecting back on itself so that an average photon will pass through the gain medium repeatedly before it is emitted from the output aperture or lost to diffraction or absorption. If the gain in the medium is larger than the resonator losses, then the power of the recirculating light can rise exponentially. But each stimulated emission event returns an atom from its excited state to the ground state, reducing the gain of the medium. With increasing beam power, the net gain reduces to unity and the gain medium is said to be saturated. In a continuous wave laser, the balance of pump power against gain saturation and cavity losses produces an equilibrium value of the laser power inside the cavity. This equilibrium determines the operating point of the laser. If the applied pump power is too small, the gain will never be sufficient to overcome the resonator losses, and laser light will not be produced. The minimum pump power needed to begin laser action is called the lasing threshold. The gain medium will amplify any photons passing through it, regardless of direction, but only the photons in a spatial mode supported by the resonator will pass more than once through the medium and receive substantial amplification. The light emitted, the light generated by stimulated emission, is very similar to the input signal in terms of wavelength, phase, and polarization. This gives laser light its characteristic coherence, and allows it to maintain the uniform polarization and often monochromaticity established by the optical cavity design. The beam in the cavity and the output beam of the laser, when traveling in free space rather than waveguides, can be approximated as a Gaussian beam in most lasers. Such beams exhibit the minimum divergence for a given diameter. However, some high-power lasers may be multimode, with the transverse modes often approximated using Hermite Gaussian or Laguerre Gaussian functions. It has been shown that unstable laser resonators produce fractal-shaped beams. Near the beam waist, it is highly collimated. The wavefronts are planar, normal to the direction of propagation, with no beam divergence at that point. However, due to diffraction, that can only remain true well within the Rayleigh range. The beam of a single transverse mode laser eventually diverges at an angle which varies inversely with the beam diameter, as required by diffraction theory. Thus, the pencil beam, directly generated by a common helium-neon laser, would spread out to a size of perhaps 500 kilometers when shone on the Moon. On the other hand, the light from a semiconductor laser typically exits the tiny crystal with a large divergence, up to 50 degrees. However, even such a divergent beam can be transformed into a similarly collimated beam by means of a lens system, as is always included. For instance, in a laser pointer whose light originates from a laser diode. That is possible due to the light being of a single spatial mode. This unique property of laser light, spatial coherence, cannot be replicated using standard light sources, as can be appreciated by comparing the beam from a flashlight or spotlight to that of almost any laser. Quantum versus classical emission processes. The mechanism of producing radiation in a laser relies on stimulated emission, where energy is extracted from a transition in an atom or molecule. This is a quantum phenomenon discovered by Einstein, who derived the relationship between the A coefficient describing spontaneous emission and the B coefficient which applies to absorption and stimulated emission. However, in the case of the free electron laser, atomic energy levels are not involved. It appears that the operation of this rather exotic device can be explained without reference to quantum mechanics.